Now let's take a look at a rolling problem where we apply a force at the center of mass of a rolling disk. And let's see if we can determine the force of static friction as well as the acceleration of the center of mass of the disk. So here's our disk, and we're applying force at the center of mass, and we want to know what the force of static friction is at point of contact P. Now again, it's rolling without slipping. So I'm going to take a guess that the force of static friction acts to the left. It's a disk, radius r, mass m, ICM is equal to 1/2 m r squared. Using Newton's second law of translation, or for translation, we see that the force, this force minus the force of static friction, should be equal to the mass of the disk times the acceleration of the disk's center of mass. Now what I'm going to do is apply Newton's second law for rotation, and I'm going to apply about point P, thus eliminating the need to worry about the torque exerted by friction. So the sum of the torques about P would be F times lever arm R is equal to the moment of inertia about point P would be the moment of inertia about the center of mass, which is 1/2 m r squared, plus the mass of the disk multiplied by the perpendicular distance between the two axes of rotation, okay, one through point P and one through the center of mass. So that's mr squared. And then alpha would be ACM over R. You'll notice that the R's cancel. So we're left with F is equal to 3/2 m times ACM. Okay. So the force is equal to 3/2 mass of the disk multiplied by the acceleration of the center of mass. So the acceleration of the center of mass then would be equal to 2/3 F over m. How about the force of static friction? Okay, I'm going to take this equation, solve it for ACM, which I did, and then substitute it into this expression here. So I'll take this and substitute it into this expression. So I have F minus the force of static friction is equal to m times 2/3 F over m. The m's cancel. Force of static friction then is equal to 2/3 F negative plus F, which gives us 1/3 the force applied at the axle. So my guess that the force of static friction acts to the left was correct, because if it wouldn't have been correct, this would have came out to be negative. Notice that this is the magnitude of the force of static friction is equal to the magnitude of the force over 3. So it should be a positive quantity. And since it is, then the force of static friction is indeed to the left. And what I'm going to do now is demonstrate this using the same apparatus I used previously. Okay, so here's the disk, and I have the string attached to the center of mass as shown. I'm going to place it on this low friction cart here. And what I'm going to do is I'm going to exert a force to the left. Now, according to the theory, the force of static friction would act to the right. So that means, from Newton's third law, that there should be a force to the left on the gray cart. So the gray cart should accelerate to the left when I pull the disk to the left. Okay, so here we go, 1, 2, 3. And you can see it did that. Okay, so the force of static friction on the disk is in the same, no, it's in the opposite direction of the force that we apply at the axle.